Hello, I am going to be going over an introduction to frequency response in circuit analysis. So to begin with, the outline for this is going to be some introduction concepts of the transfer function itself. Next, I'm going to take a look at how do you derive the frequency response of a simple RC circuit. So, when you're learning these critical concepts, at first you just need something really simple, or else otherwise it could easily become overwhelming. Next, I'm going to define some critical base frequency. The critical base frequency is just a frequency, like a reference frequency that you're going to need in order to say, what am I going to base my other critical frequencies off of, from. Next, I'm going to calculate some critical points, and then I'm going to simulate the circuit and plot those points. So I'm going to use a circuit simulator for that and plot those points. And then last, of course, I'm going to compare those calculation points, what I calculated here with the calculating the critical points, and then I'm going to compare that to the simulation. And then we're going to see how that comes out to be, if it's accurate, if they agree or not. So, introduction. Okay, so if the amplitude of a sinusoidal source remains constant and you vary only the frequency, you have the circuit's frequency response. Okay, so that's what it is. So the frequency response is a complete description of the sinusoidal state behavior of a sinusoidal steady state behavior of a circuit as a function of frequency. So as you know, there's a transient state and then there's steady state in circuit analysis, and you're just only dealing with the steady state part of this and all of this analysis here. You don't deal with the transient. That's really the whole response. But with this type of analysis, you're only considering the steady state because that's all that really matters based upon your goal of understanding its steady state behavior. By the way, amplitude, magnitude, I pretty much use those interchangeably. So if I say amplitude, I mean magnitude as well. Magnitude, I mean amplitude. No real distinction between those two as far as I'm concerned, not with what I'm talking about in this in these slides here. Okay, so that's the introduction. So next, the transfer function. So okay, what is it? Well, the transfer function h of s is also called the network function. It's also called the network function. S is a more general S domain variable, and for the frequency domain, it's evaluated at S equals j omega to transform it into a phasor expression. Just one little note here. It is omega, but I'm just going to start saying W because it looks very much like a W. If I say W, it's easier to see that, okay, that symbol. If you say omega, we don't speak Greek, so it's kind of foreign to us. So I try to get as close to the goal as I possibly can and simplify how I explain things as much as I can. So I'm going to say W. So when I say W in these lecture slides of mine, what I mean is omega. Okay, so again, S is the more general S domain variable, and for frequency domain, you're going to be evaluating S at JW to transform it into a phasor expression, because ultimately you're going to need to have it into a phasor expression. When you have it into a phasor expression, then that's basically the end goal, because a phasor is going to do what? It's going to tell you the amplitude and the phase of that particular quantity. Okay, so now we have h of JW And note, some books just leave it as H of W, but it means the same thing. So, you know, these things, these are just conventions, and it is good to know what the main convention is, but they are just conventions after all. So that's what that shows. Because some books, you know, if you, depending on the book that you read, you may see H of JW or you might see H of W. W varies from 0 to infinity. As you know in mathematics, you cannot include infinity with a closed, a boxed bracket, like a square bracket. You can't. Even though, in spite of that, I still see it in books that they'll have infinity included, but you actually can't include infinity in a range. Infinity is I don't know, maybe with number theory, maybe possibly it's not even classified as a number. But anyways, definitely mathematically, it is incorrect to include infinity, either positive infinity or negative infinity, either way. But W does vary from 0 all the way to positive infinity. So next, H of JW is going to be equal to Y of JW divided by X of JW. Now, what are those? Y of JW is the output phasor voltage or current. X of JW is the input phasor voltage or current. So what this means is basically it's output divided by input. That's basically what the whole transfer function in and of itself is. And then last bullet point on this slide, H of JW is a ratio of circuit output to circuit input, which is basically what I just said. Okay, so that's just a repeat of that. That's just a summary point. Okay, so next, going on to this, the transfer function. So, you know, another summary of this is that the transfer function applies only to linear networks. So if there's a non-linear network that you have that you're considering, the transfer function analysis does not apply to that. But even for non-linear devices, they're used to ultimately use them in their linear range so that you can make a linear device out of them only within their range, you know, particularly transistors. Okay, but the transfer function applies only to linear networks. Now, this linear network, as you can see here, this is another summary. You have X of S input coming in. You have the linear network H of S, which, you know, this is in a general S domain form. H of S is that linear network. Okay, it's the machine. It's the machine inside of that box. Whatever components are in that circuit, whatever makes up that circuit, that's mathematically represented as H of S. Okay, its characteristics mathematically. And then you have Y of S as an output, and that is just, you know, your output variable there. So when you transform that and you go into the phasor form of it, all you're going to do is simply substitute JW for S. And again, it only applies to linear networks, and that's in the phasor form. When it's in its phasor form, then you can actually start doing calculations and things like that. So transfer function. Okay, so since the input and output can either be voltage or current, there are 4 possible transfer function combinations. Okay, so these combinations are voltage gain, which is V out over V in, current gain, which is I out over I in, transfer impedance, which is V out over I in, and transfer admittance, which is I out over V in. The V out over I in, depending on the subject area that you're in, you might see that as trans resistance, particularly for amplifiers, you know, trans resistance, or maybe they may call it transimpedance, but that's basically what that is. And then the other one here, transfer admittance, you might see that as transconductance. But those are still, basically the same concepts there. Going back to the V out over IN, why would you call it a transfer or a trans resistance or a transimpedance? Well, simply because V over I gives you R. Down here with the transfer admittance, I over V gives you a conductance instead of a resistance. So that's where transconductance comes from. So next, H of JW is a complex quantity, so it has magnitude and it has phase. Okay, all complex quantities, whether they're in rectangular form or if they're in polar form or if they're in the exponential form, they have information for magnitude and phase. It's just that when it's in a phasor form, which is a polar form, it's easier to see it and it's easier to work with. It's more intuitive. But the rectangular form with the real part and the imaginary part still contain that data, obviously, because you go from the rectangular form to polar and vice versa, or you go into the exponential form, but those are your three forms. The phasor notation is the absolute value of H of JW, and you have your angle symbol followed by your angle, your phase angle, which is phi. Next, note that some books will distinguish H of JW from the absolute value of H of JW by using bold versus non-bold font, but using H of JW for both. Now, I don't particularly like that. In reading books, I've never liked it. Sometimes you're not looking at things in a very meticulous way. You miss it, and they're talking about the magnitude of something rather than the whole entire function itself, and that throws you off. So I put here in my slide that I like to avoid ambiguity, so I use absolute value brackets so that there is no misunderstanding of what I am talking about. I mean, you maybe can understand, like, oh, well, I see the bold face print, I understand it, but it's a bit too subtle as far as I'm concerned. I like for things to be simple and as unambiguous as possible. So anyways, plus it is correct mathematical notation to use the absolute value brackets. That's in your math book. I think that book authors choose a more simple expression over one that has more writing involved. So just using the bold face print, will involve less writing, but I don't use it. Well, not in my slides. I'm not going to use it. So anyways, the transfer function, moving on. If the numerator of h of s is 0, the root of the numerator, this is called the 0 of the transfer function because it results in a 0 value of the function. If the denominator of h of s is 0, which is the root of the denominator, this is called the pole of the transfer function because it results in an infinite value of the function. They'll tell you about roots of the numerator. As far as I'm concerned, it's just an equation that equals 0. So, you're just going to do some algebra and figure out what makes the numerator 0. You're going to do some algebra, what makes the denominator 0, and those are going to be your answers for your zeros and your poles. So moving on next to an actual circuit itself to analyze. So I'm going to find the transfer function of the RC circuit here. Okay, So this RC circuit is very, very basic, very, very simple, and that's how you want to start off. So remember that the impedance of the capacitor in its most general form is 1 over SC. The impedance of the resistor, these are both in the S domain. The impedance of the resistor in the S domain is just simply R. And then when you do an L transform to transform your voltage that's coming into it in the time domain, you're going to have voltage in the S domain. So it's just a matter of notation there. Next, so VC of S is going to be our output of our circuit. So let me go back to point that out to you. So right here where we have this capacitor on the right side, that's going to be the output of our circuit, okay? So that's why I said VC of S. It's in the S domain. VC is going to be our output. This is going to be our input VN, which is, you know, in the simulator, it's V1. And so let me go back to where I was before. Okay, so using the voltage divider rule in the S domain, that's simply just going to be V out of S equals 1 over SC divided by 1 over SC plus R times Vn of S. And so you're going to reform this, and the major goal of the transfer function is to get V out over Vn. So you're going to reform the equation to have V out over Vn. And when you do some more reformation to the numerator and denominator, it's going to simplify to that. And that's H of S for this particular circuit. Next, to get the magnitude and phase information, evaluate H of S at S equals JW to transform it into a phasor. And so H of JW is now just simply, as you can see, you put in place of that S, you put JW. For phasor magnitude, what you're going to do is, okay, you're going to have your absolute value of H of JW. That's going to equal the numerator, the absolute value of the numerator divided by the absolute value of the denominator. For this particular circuit, that gives you 1 over the square root of 1 plus WRC squared, all as one thing squared. So that's going to be your phasor magnitude for this particular circuit. Now for the phasor phase in this circuit, you're going to have the angle of HJW, or rather the angle of H of JW. Then you're going to have pretty much about the same setup here. You're going to take the angle of the numerator and you're going to divide it by the angle of the denominator as a phasor quantity. And these are phasor type angles. So when you do that and you use phasor math to do that, you're going to end up with negative arctangent of WRC. Okay, so that's going to be your angle is going to be negative arctangent of WRC, and that's basically going to be that. Okay, so the complete phasor transfer function expression for the RC circuit is this. So you just put those two major big pieces together and that's what you have. So this is your complete phasor expression. Okay, so now I'm going to get into the evaluating the function. Okay, because now we have the function. Now what are we going to evaluate it at? I mean, when you plot this all out, then like on computer, then you're gonna tell it how many points per decade, or if you're doing this linear wise, you're going to tell it how many total points, and then the computer's going to do all that work for you. But that is very, very tedious for a person to do this, even just with a calculator, to keep doing that, over and over again to get, several points on it. And it's even worse if you don't have a calculator. So we're going to, talk about these critical points so that you don't have too many of them to plot. You just want to get the critical points. You don't want to go through all of that trouble to plot points that don't differ and are not critical, and the function doesn't really change for those given frequencies. So when evaluating the function, there are critical frequencies of interest. The RC circuit has a critical frequency that is defined in terms of RC. So that makes sense to me. It's just like how you define the constant itself, pi. I mean, what is pi? Pi is the circumference versus the diameter of a circle. It's a ratio between the circumference versus the diameter of the circle, and it's a constant because the bigger that the circle gets is the bigger that the diameter gets, the bigger that the circumference gets, but the ratio between the two does not change. And that's what you have as pi. So I like things like this that say, we're defining something based on the intrinsic values of whatever it is that we're dealing with. And so the base critical frequency is W0 equal 1 over RC. Now, I've heard people say omega naught. And anytime there's a subscript of 0, they pronounce that naught. And I have no idea where that came from. I don't think I've seen it in books too many times, but I don't like to get hung up on pronunciations and vernacular, because this is engineering. Who really cares about pronunciation and vernacular? The main point in engineering is that people understand you. So I don't say omega naught. I would say omega 0. Okay? But in my opinion, you really shouldn't even use 0. You should use like omega C, for critical, like critical frequency. But again, going back to how I was talking before, I'm going to call that W. So I'm going to say W0. So the base critical frequency is W0 equals 1 over RC. And we'll get to why you can use that and how it makes sense. So at a minimum, there are 3 critical frequencies that you want to plot, or you want to calculate when you're matching up plots. But, so at this, at a minimum, you need 3 of them. The first one is when omega equals omega 0 divided by 100. Now remember, omega 0 is a constant. Omega is not. It's the variable. So when omega is equal to omega 0 divided by 100, okay, then that's the start of your range. And for this particular circuit, this is approximately like 0 dB in magnitude. So that's that's just the characteristic of this circuit. And so next we have omega equals omega 0, or W equals W0. Now that's special because it's a major inflection point on the whole function itself, and it's by the way, it's negative 3 dB in magnitude. Now again, I'm not going to get into dB, not in these lecture slides, but I'm just making a side note of that, just so that you can cross-reference this information later when you do get into dB. Next, W equals 100 W0. That's the range end of all of this, and beyond that, it really doesn't make sense to go any further, because basically you're going to be at the end of your range, and that's correlated to like negative 40 dB in magnitude for this particular circuit, for this RC circuit. Okay, so at a minimum, you're going to be calculating those three frequencies for the transfer function itself. And again, W0 is going to be equal to 1 over RC. So for your circuit, if your circuit has different values of RC than somebody else's RC circuit, then your W0 is going to be different from their W0. And then that's going to, in turn, impact your starting range, your inflection point, and your range end. Okay, so that's how that works. Okay, but this is reasoning in terms of symbols, which is a more generalized form of abstraction, and it's going to be very general, and it's going to apply to all RC circuits for this type of analysis. So next, the function is most often expressed as this. Now, when you read books, you're going to see this. I can guarantee you, you're going to see this. And we just, I'm going to go back a couple of slides here. We derived it and we get this. Okay, we have WRC here. Just concentrating on that part there. We have WRC. Now, where in the world, how is that compatible with what you find in books? We have W over W0. Okay, and here's the explanation to that, which, by the way, I haven't seen it in any books that I've read so far, or at least I don't remember that I did. But they don't provide you with an explanation of that. They just simply throw it out there and say W over W0. But this can be used. They're right now, but they don't explain themselves. This can be used because W over W0 equals W over 1 over RC, which equals WRC. Remember now, W0 equals your 1 over RC. And so W over W0 is just an alternative expression of WRC, so long as W0 equals 1 over RC. And that's that. If they for this circuit, if they define W0 any other way, then that's some totally different other thing. So I don't even know how that would work out, but it's defined as being 1 over RC. Next, you may use W or F for plotting. Now, what in the world, W versus F? What in the world is W versus F? Well, eventually I'll get to that point and I'll show you the difference between those two. But for right now, just know that they are both frequencies. They are both frequencies, okay? They really only differ by a scalar amount, a constant amount of 2 pi. Okay, but they are both frequencies. I mean, some books, I think they call W omega an angular frequency, but nonetheless, they both represent frequencies, because ultimately W encompasses F, and I'll get to that in a couple of more slides probably. So anyways, you may use either W or F for plotting. For plots shown in books or drawings, omega, which is W is usually used. Remember that W0 equals 1 over RC for this particular circuit. In the RC transfer function expression, this is your expression here. When W equals W0 divided by 100, you're approximately at about, you're at the low end of the spectrum there. So you're close to zero. Okay. And, or I really, maybe I shouldn't say you're close to zero. It depends, because your values may be different. So you're not approximately close to zero. That's not totally correct for me to say that. It depends on your values. You're at the starting end of your range is what it is. And when you're at the starting end of your range, for this particular circuit, your magnitude is going to be approximately 1. That's where I should put a 1 there. I'm seeing these little bit of these inaccuracies here now as I'm going, but I'm explaining it. So anyways, I'm self-correcting there. So it's not that you're necessarily approximately 0 hertz or 0 in your frequency. Your radian frequency, or your angular frequency. It just depends on your values, but you're at your starting range in your analysis for this. This is a good starting point, lower limit to start plotting points for this function, is what that means. And so your function is going to be, absolute value of h of jw, your angle with your angle measure in there, and that's going to be equal to, it's approximately, but let's just say it's going to be pretty much equal to 1 with an angle of 0 degrees. By the way, these are always in degrees when they're expressed in phasor form. I could put a little circle up there, but I should. But anyways, I'll keep moving on. I'm just explaining that to you now. In another revision, I'll have to correct that. When W equals 1 times W0, you get W0. That's simple. And you end up with 1 over the square root of 2 at an angle of negative 45 degrees. So I have my degree sign there. Okay, so I just need to correct it there, that's all. Moving on. Next, when W equals 2W0, then you have this situation. You have 1 over the square root of 5 at an angle of negative 63.43 degrees. When W equals 3W0, you have this, 1 over square root of 10 at an angle of negative 71.57. When W equals 10W0, then you have 1 over the square root of 101 at an angle of negative 84.29 degrees. When W equals 20 times W0, you have 1 over the square root of 401 at an angle of negative 87.14 degrees. And then when W equals 100 W0, then you have 1 over square root of 10,001 at an angle of negative 89.43 degrees. So you see how being at like 100 is pretty much sufficient to pretty much, get the point of like where this is going. Your magnitude is getting really, really small here because the denominator just keeps increasing. And over here, it looks like you're heading towards negative 90 degrees. But it seems like the closer it gets to it, the more it slows down, because that becomes a stopping point. So it's good to see these trends and to pick up on it and see, how that, how you develop some more intuition about all of this with this particular circuit. Then when W approaches infinity, like I just said, you're going to get to 0 at an angle of negative 90 degrees for your transfer function. Or for your, it is your transfer function in phasor form. Okay, so for plotting in general, you might need to use frequency F rather than W. Now this is where I get into the relationship between the two of those. The relation is just simply W equals 2 pi F. Okay, so then you have F equals W over 2 pi when you do some algebra there. Very simple algebra. And then you have W0 equals 2 pi F0. It just follows the same way. So therefore, F0 equals W0 over 2 pi, right? And what is W0? W0 is 1 over RC, and then that simplifies to 1 over 2 pi RC. So F0 is equal to 1 over 2 pi RC. That's what F0 is, and you're going to need to use that when you come up with, different calculations. So for plotting in F rather than W, you're going to replace W over W0 with F over F0 because, and this is why you can do that, is because W over W0 equals 2 pi F over 2 pi F F0, and then that's going to equal F over F0. So you can just replace, W over W0 with F over F0. That's your summary point there. Next, in the RC transfer function expression, which is this now, see how I, replaced it there. You have F over F0 here, okay? And you also have F over F0 here. So when you evaluate this expression at these critical points, when F equals F0 over 100, again, it depends. Depending on your values, the values that I used in the circuit that I simulate, you are at approximately 0. But again, that could vary for you if you have different values for R and C. But at the very least, it's at your lower limit of what you're evaluating. So that's going to give you, regardless of where it's at, it's going to give you a magnitude of 1 at an angle of 0 degrees. Now, just as a side note, not to get into it, whenever you have a magnitude of 1 and you calculate a magnitude in terms of decibels, in terms of dB, that's going to be 0 dB. So that's just a side note. Now, next, when F equals 1 times F0, which is F0 itself, okay, so when F equals F0, what are you going to get? Same thing, and as when you were using W, and you should, and that's basically it. So this is a good kind of like checking point for consistency. So you're going to get 1 over square root of 2 at an angle of negative 45 degrees, and 1 over square root of 2 is approximately 0.707 at an angle of negative 45 degrees. Next, when F equals 2F0, all of this is going to be the same as when you were using W, but we, go over it again anyways. You're going to have 1 over square root of 5 at an angle of negative 63.43 degrees, and that's approximately a magnitude of 0.45 for your 1 over square root of 5. When F equals 3F0, then you're going to have 1 over the square root of 10, which is at an angle of negative 71.57 degrees. 1 over square root of 10 is approximately 0.32. That's going to be your magnitude there. And when F equals 10F0, you're going to have 1 over square root of 101 at an angle of negative 84.29 degrees. And your 1 over 1 over square root of 101 is approximately equal to 0.1. When f equals 20 times f0, then you're going to have 1 over the square root of 401 at an angle of negative 87.14 degrees. And 1 over square root of 401 is approximately 0.05. That's going to be your magnitude. When f equals 100 f0, you're going to have 1 over the square root of 10,001 at an angle of negative 89.43 degrees. You see how it's just about there at negative 90, but the trend shows that it's slowing down. It's like it's about to come to a stop at negative 90 degrees. Okay, and your 1 over square root of 10,001, again, that's at an angle of negative 89.43 degrees. So you can clearly see that as f approaches positive infinity, you end up with 0 at an angle of negative 90 degrees. Okay, that will end my slide lecture, and now I am going to get into some simulations and comparisons. That's the next part. Okay, so for the simulation part here, I'm using Multisim for the circuit here, and then I'm going to be using FreeMat in order to calculate values for the critical points of interest that we're calculating them at. Okay, so in this circuit here, you can see that, I have my RC circuit here. My resistor is at 1 kilo ohm, and my capacitor is at 1 microfarad. I chose these values because they're pretty typical. They're not hard to find. You usually see these as like real values that you have in real components. So I chose it for that reason. And then I just simply use 1 volt for a peak for my sinusoidal input. And then my output is over this capacitor here. And this probe is with respect to ground, so it's as good as being between here and there, just across the capacitor. So again, 1 kilo ohm for my resistor and 1 microfarad for my capacitor. So for the plotting, over here in FreeMat, what I did do was I came up with a script, and the script here, it clears, it clears to clear the variables, and CLC is to clear the console. So clear the variables, clear the console. That's just a normal practice for me at the start of any script that I usually write, just to make sure that there, just in case I ran a previous script, there's nothing that's going to interfere with anything pertaining to the script that I'm trying to run here. So next, in my code here that I wrote, is that I calculate data for the RC circuit frequency response. And again, R is at 1K, C is at 1 micro. My F0 is going to be, just like according to the slides, it's going to be 2 pi times R times C. And for my magnitude function here, just as we calculated in the slides, or derived in the slides, just how we have them in the slides, it's going to be 1 over the square root of 1 plus f divided by f0 squared as a unit itself. And that's going to calculate my magnitude in this circuit here. Then for the phase, it's going to be the negative arctangent of f over f0. Now, in FreeMat, you're going to need to put in, a tan d, and what does the d represent for degrees? Because you want to get your result back out in degrees. You want to use the arctangent function, but you want it to be in degrees. The A in the front of the tan is just for arc. So arc tangent, giving you your result back in degrees. And we need to get the negative of that, right? According to what we derived in the slides. Okay, so next, I call this F start, and I have to call it F start because I can't name it F0, you know, because then that's already taken up with, you know, F0 here. That's already been defined. Like I said before, back in the slides, I think it would be a better convention to say FC, to use F critical, you know, like FC instead of F0. But you will find in books that they use W0 or F0 for the critical inflection point frequency, and I think that it makes better sense to just use FC. I don't know, maybe going forward into the future, if I see a need to, then I might just start using FC. If not, then I'll just stick with their convention. But I think that their convention, it's possible that it could use some improvement, but I don't know. I'll have to keep going on and seeing more and more and more to see whether or not this makes sense in the long run or not. So anyways, so that'll be my F start, F0 over 100. My magnitude will be according to this function. So that's a good reason to write a function. And in FreeMat, you know, you write a function by saying, you know, whatever your function name is equals at, and then you put parentheses, and then you put your arguments in there, and then you put the function over here. Now, that's a function that's in the script itself. I like using those functions as opposed to using functions that you have to make sure it's in the same folder as that script that needs to use it. I just like having the function, you know, integrated into the script itself. So that's the syntax anyways for doing that. And then so next, F1, I can name that F1 now. So F1 is in a magnitude, is in a multiple of F0 by multiplying it by 1. And so I calculate that using my magnitude and phase functions that I wrote in the script, you know, here. And so I just keep using those over and over again in every calculation that I do. So F2 will be 2 times F0. I calculate that magnitude and phase based on, you know, F2. F0 is never going to change, but I included it as a argument in my function anyways. F3 is going to be 3 times F0. We're going to get a calculation for that. F10 is going to be 10 times F0. We're going to get a magnitude phase calculation for that. And then F20 is going to be 20 times F0. We're going to get calculation for that. And then the same thing for F100. We're going to get a calculation for that. So let me go ahead and run this. So I'm going to hit execute the current buffer. Basically, that means run it. And we're going to see these values come up here in the console window. So this is the output of that script once it's been executed. And so what do we have? So F start is going to be 1.5915. So in our simulation over here, what we want is we want to make it start at that value. And then we're going to look at magnitude, phase, and we're going to keep looking at magnitude and phase for these various frequencies over here in our simulator when I simulate it and bring up a plot for that. And so that's all our data that we're going to look at over here, look at, you know, in our simulator based upon what we calculated over here in our script. So let's go over here to our simulator, and in the simulator I'm going to want to go to, like a simulation and, analysis and simulation. This is in Multisim. And you have all these different things, but we're on AC sweep. So we're going to do an AC sweep, and F start is at what? 1.5915. Started at 1.5915. We can take out that 5 there. And then our terminal frequency is going to be at 1.5915 times 10 to the 4. So that would be what, like 4 decimal places. 1, 2, 3, 4. So that would be 15,915. So 15,915. We put that in units of hertz. It'll convert it, So go back over here. Let's see, simulate, analysis, and simulation. So it converted it, to put it over here, and it did the drop down menu for us. That's automated. So it's 15.915 kilohertz. That's going to be the end of our range in this analysis. Now the next thing is sweep type. We can use decades, octave, or linear. I'm going to use decades. All that it is that it's just a horizontal scaling of how things are going to be horizontally scaled. You'll see it'll be like the major points will be like 1 and then 10 and then 100 and then 1,000 if we go that far, and so forth. And that's plotting it over decades, and it's not a linear horizontal scaling. But the reason why they use that is because for these types of circuits, it's easier to look at and see inflection points on it. And that's what I gather from it. I mean, I didn't read that in a book, but it's just what I see. And I think that makes sense to say we'll see when we plot it, okay? And actually, I'll do it both ways, okay? So anyways, number of points per decade. I think a good number to put in there is about 20. I mean, you could put in more. It depends on the accuracy of what you're trying to plot and the range and everything. If the range is really small, then you probably need more points. If the range is really large, you probably need less points because you have more of a range to cover. But I'm just going to keep that at 20. And then the vertical scale, I'm going to keep that linear. The choices are, you got linear, logarithmic, decibel, and octave. But as said before, I'm, for the scope of what I'm trying to cover here, I'm going to keep that simple and just keep it to linear. And then you'll see, that, the results that we get over here should be consistent with the plot itself. So that's just the AC sweep setup. Now the output says V parentheses PR1. Well, what in the world is that? Well, that's the voltage of probe 1, and this is probe 1. It's the only probe in the whole design, so there's no other choice. So it's clear that that's the voltage of probe 1, and that's automatically implied that it's with respect to ground. So it's across this capacitor here. Okay, so with that being said, I'm going to just hit run and let's see what the plot looks like. Again, decade, linear. Let's see. So this is the plot. Let me resize the window. So you can see that this is the plot. This is what it looks like now. And so up here you have magnitude, down here you have phase. Okay, you got magnitude and you got phase. And so like I said, when you deal with decades, you see the spacing here, that's not linear, because there's a lot of space here, little there, less there, less, up until you get to 10. but that's easier to look at. Now, I'll say it like this. Let's go back and redo the simulation, but let's look at it in terms of linear, the sweep type, linear, and let's see. Now, that is you know, linear, like between 0 and 2K and 4K and 6K. You know, these steps are linear, but look what the graph looks like. It doesn't. It's a matter of you know, converting this into something that gives you more intuitive information on it. And by the way, I mean, like, you get like these kind of like hard straight lines because what you would need to do if you wanted to run it like that is you need to put more than 20 points on the whole graph. So this is not per decade. It's talking about how many points on the whole graph. And I think at a bare minimum, it should be 200 or more, somewhere between 200 to 1,000. I think 1,000 would probably really start overworking your computer. It just depends on your processor. But I think 200 is sufficient enough. Let's see. Yeah, see how it smooths out a little bit more. And in this program, you do have the ability to, you know, different zoom types. And so you can, there's a window zoom. So you can zoom close in and you can see how fine that line is, at least at that level. That's like a sharp bend, but let's go back to the original zoom amount, and that's what it is. So when you go across it linearly, it doesn't give you, you know, the type of graph that you really want to see. So I'm going to go back and I'm going to go to reevaluate it and resimulate it. Those graphs are saved, by the way. They're, you know, in those other tabs, the previous tabs, but I just rerun it and see what it does. But let me make sure that well, it's already processed, but let me go back again, and you see numbers of points per decade. I don't need 200 points. 20 is sufficient, but let's just make it 50 points per decade. And that's what I have. So anyways, getting back to the comparison and the analysis. So this is per decade, and that's not going to make a difference on the value of what it is when you get to, you know, what you're trying to get a value for. It's just a matter of what it visually looks like, but it doesn't change the result of it. So you go to cursor and X value, and so let's see. Let me, you know, resize this window so that we can see our results over here for comparison's sake. So let me just resize this. Okay, so first part of this, F start, that was at 1.5915. So what you do is you go over here onto your cursor and you say, you know, first of all, make sure that you select the cursor that you want. For me, that's cursor 1. Keep it nice and simple. X value. See, cursor 2 is off over here. Okay, because what I did was I pulled it off of the graph outside of its range. When you do that, all of that disappears and it looks more simplified. So it's easier to exactly know what you're looking at. So F start 1.5915, and it goes to that value, but that's cursor 2. So take that back, go to cursor 1, cursor X value, again 1.5915. And what do we get? So the magnitude, I'm on this magnitude graph here. What is that? it's 999.950 milli. That is approximately 1. Okay, so our magnitude here is 1. Our phase is negative 0.5729 degrees. That's pretty close to 0. Okay, I mean, the phase is going to be, it's going to either be 0 or negative for this particular circuit, but that negative is not that far away from 0. So anyways, let's go on to the phase part of it, just for that one same particular point. Let's take a look. So what you're going to do first is you're going to turn on the cursors for that. That's a different cursor. So I'm just going to put that down here, put this up here, just position it that way. And so for that cursor, you're going to say, I'm going to select the X value, and I want that to be 1.5915, same frequency, and it's cursor 1. So at that frequency, what do you get? Negative 572.92 milli. What did we get here? Negative 0.5729, which is, milli. If you take this milli and you convert that, you take away milli, you'll get 0.57292. So 0.572. And what do you have here? 0.572. So that checks out just fine. And that is that. So that's just for that one first frequency there. Now let's move on and let's go to the next one. The next one is going to be 159. So I'm going to go back over to here. I'm going to set the X value to what? 159.1549. And I'm going to do it for both. Go up to the magnitude graph, set the X value 159.1549. What do we have? For the magnitude, we have 0.707 in our calculation. That matches 0.707 on our graph. What about our phase? We have negative 45. On our simulation, we have exactly negative 45. That matches perfectly. Next here we have, so we're at F1, F2. That's at 318, right? So go back over here, cursor, X value, F2 is going to be 318.3. It's closer to, well, let's put all of the digits in there, right? And I'm just going to use copy on this. And let's position the phase at the same value there, at the same frequency value, because those are two different cursors. Got to do them independently. And so what do we get for the magnitude here? We get 0.447. What do we have here? 0.447 with a 2 there, That's exactly the same. What do we get for phase? Negative 63.43, 49. And what do we have here? Negative 63.4342. That's pretty much, that's not exactly the same, but that's, look how many decimal places you have. There's a difference in, past like 3 decimal places. So it's to 3 decimal places of the same accuracy. So that is very, very good. It's not exact, but it's very, very good. And so that's all you can ask for with that. Very, very, very good. So that's a pass. That's good. Next, so moving on to, we were at F3. No, we were at, because F3 is 477. Okay, we were at F3. So let's move on to F10. Okay, and when I'm doing these numbers like this, F3, 2, 1, I'm talking about multiples of the base frequency. And so we're doing 10 times the base frequency F0, and that frequency for this particular circuit is 1591. So let's go into this 1591.5494. By the way, if you do more data per decade, if you plot more points per decade, the accuracy, of course, goes up. But I did as many as I did, and it gives me a certain amount of accuracy. But to like 3 decimal places, that is really, really good. And so let's see here. So we're at F10, and F10 is at 1591, right? So let's do that here for our magnitude graph. We're going to set the X value to what? 1591.5494. Probably should have copied and pasted that. But anyways, so what is the value there? I get 99 milli, which is 0.099. I'm going to look for that over here. What do I have? 0.0995. This would be 0.0995 just as well. That's a pass. That's good. What about our phase? Calculation says negative 84.2894. What do I get over here? Exactly negative 84.2894. No problem with that. That's a pass. Let's see. Next thing we have here, that was F10. F20. 20 times the base frequency. And what is that base frequency? I'm just going to copy that out of here and paste it over here. It's on phase, but I'll go back to magnitude. Paste it over here. Or was it on magnitude? Yeah, it was on magnitude. It's just that in multisim, that marker over there that tells you where it's at is so small that it's so easy to miss. Now, when I go down here to the phase, you see the red marker there? Came down here, so now we're on phase. And put in the X value for that. And so that is that. So at F20, we have a magnitude of 0.0499. So that would be 49.9 milli. And what do we have over here? 49.9 milli with a couple of more digits there. But 49.9, that is really, really good. That's a pass. That's good to go. Next over here for phase, what do we have? Negative 87.1374 in the simulation. Come over here to the calculation. We have negative 87.1376. 3 decimal places of accuracy, of exact same accuracy. That is very good. That's a pass. Next, we're going to have, it's the last one we're going to do, F100. And F100 is at what? I'm going to copy this value that we're going to evaluate it at. Magnitude, set the X value. Phase, set the X value. It's good that it uses the same, this is why standardization is really good. It's good that it uses the same exponential expression where it's like e plus 0.004, because if it didn't, then you'd be involved in trying to convert that manually yourself, and that just puts more work on you. So anyways, we're at the end of the range here, and what do we get? So we get for magnitude in the simulation, we get 9.998 milli. So we're getting real small here now. And what do we have in the calculation? 0.01. Okay, so basically that's saying 10 milli. 0.010 is 10 milli, and what do we have over here? We're on the verge of 10 milli. So that's a pass. That's good. What do we have for phase? We have in the simulation negative 89.4270. And what do we have for our calculation? Negative 89.4271. Again, 3 decimals of accuracy there. We're all good to go. And we can see clearly that that's heading for negative 90 degrees, and this is heading for 0 for magnitude. Okay, so I went over, several points here, but at the very least, you need 3 points. The starting of the range, you're going to need over here, and the ending of the range you're going to need over there, and then some critical point in between that defines the start of a transition. And that's basically it. So that's it for this circuit analysis. And I could plot it into decibels, and I'll do that really quick, even though like I said, I'm not going to get too much into decibels, but I'll go ahead and I'll do a decibel plot, and we'll take a look at that, just to show what it's going to look like. Put that in decibels. Number of points per decade, leave that at 50. So it's decade, decibel, and see what that looks like. So you see how you have these more, this more kind of like straight looking line. That's easier for people to look at and say, oh, okay, I can see that's an inflection point. So that's, one useful part of plotting it in that way. And then another useful part to it is that anytime that you see 0 dB, it means that there is no gain. It means that what you put in and what you get out is the same. There is no gain at 0 dB. It doesn't mean that the output is 0. That's not the case. It means that there is no gain. Anything above 0 is a gain. Anything less than 0 is attenuation. Anything that is at 0 is neither gain or attenuation. It is just what same as the same magnitude as what you put in on your magnitude plot here, and that's all that is. Decibels, of course, don't apply to phase that is put in degrees, and I'll go back to the previous graph and you'll see that it's exactly the same here. Okay, so the only thing when I'm switching back and forth between these two graphs, if you look at just the phase plot and you just look at that, don't worry about the magnitude plot, just look at the phase plot, nothing changes. So decibels don't apply to phase, they only apply to magnitude. And so when you look at the magnitude here, you see that the scale differs. You go from, like, what you get is what you put in, equals 1. It's unity here on the linear scaling over here, but then the interpretation of that is 0 here on your decibel scale. And let me get rid of that. I'll just show you right here. Take number 2 off, simplify it, drag 1 like really low down here, and as you can see, like negative 513 micro, you're very, very close to 0. Okay, you get further away from 0 as you go along. You see how you get like negative 18 dB, and as you get closer to 0, we didn't go all the way down to 0, but you're talking about getting so close to 0, negative 432 micro, that's basically where you're at, from 0 for these really low frequencies. And 0, again, corresponds to a magnitude of unity between input and output magnitude. You know, in other words, you input a 1, you get out a 1. You don't get attenuation and you don't get a boost. You don't get gain. Okay, I guess that's enough said about that. So that is it, and you know, I'm not going to get all the way into dB on this video, on this lecture. That'll probably be the next one. But until then, that does it for the analysis, and you know, that's pretty much it. So all of that has been confirmed. We went over the theory of it and everything. It matches with the simulation. It matches with the calculation. Well, the calculation is based on the derivation of it, and then that matches with the simulation. So we've covered it all, and that is it right now for this video. So thank you for watching, and hopefully it was helpful for you, and have a nice day.